In 2016, the global battery industry treated sodium-ion technology as a dead end. Sodium stores less energy per unit of weight than lithium, and almost every major manufacturer limited sodium-based cells to low-power uses such as golf carts and backup grid storage units. Inside this climate, CATL, the world's largest electric vehicle battery manufacturer, began developing sodium-ion cells specifically for passenger vehicles, a segment competitors had already written off for this chemistry. Over the following years, CATL committed close to 10 billion RMB to the project and produced roughly 300,000 test cells during development. This scale of testing was unusual for a chemistry that most of the industry had abandoned. By 2021, CATL released its first sodium-ion battery product, making it the first major battery manufacturer to bring sodium-ion cells to market for commercial use. In April 2025, at CATL's first Super Tech Day event, the company introduced a new sodium-ion battery brand called Naxtra. CATL's Chief Technology Officer for sodium-ion batteries stated, "Sodium-ion is no longer confined to laboratories." This statement carried weight because CATL already supplies battery cells to Tesla, BMW, and Mercedes-Benz, meaning a production-ready announcement from the company has direct implications for vehicles already on the road. To understand why this announcement matters, it helps to look at the limitations of current lithium-ion electric vehicles. The first issue is charging time. Most electric vehicles take significantly longer than 5 minutes to charge, often requiring 30 minutes or more at fast charging stations, with charging speeds frequently reduced as the battery approaches full capacity. The second issue is cold weather performance. When a typical electric vehicle is parked in temperatures around -20 degrees Celsius, its usable range drops sharply, particularly when the cabin heater is running. The third issue concerns lithium itself. Lithium carbonate prices reached a peak of more than $70,000 per ton in 2022, before falling sharply afterward, and this volatility directly affects vehicle pricing. According to the International Energy Agency, IEA, by 2030, approximately 85% of the world's refined lithium will come from just 3 countries, concentrating supply in a small number of locations. The fourth issue is battery degradation. Over time, lithium-ion batteries lose capacity, and replacing a degraded battery pack can cost as much as the price of a used car. Naxtra is positioned by CATL as a direct response to each of these issues, built on a different chemistry rather than an incremental improvement to existing lithium batteries. The first difference is the raw material. Naxtra uses sodium derived from salt, one of the most abundant materials on Earth. This composition eliminates the need for lithium, cobalt, and nickel, removing dependence on the 3 countries that the IEA identifies as controlling most lithium refining. The second difference is charging speed. CATL states that Naxtra supports peak charging rates of up to 5C. For comparison, a competing company, Hina Battery, has reported that its sodium-based truck battery can fully charge in approximately 20 minutes, a figure relevant for commercial vehicles such as semi-trucks. The third difference is cold weather performance. CATL claims that Naxtra retains 90% of its usable capacity at -40 degrees Celsius, a temperature at which standard lithium-ion electric vehicle batteries typically lose most of their functional range. CATL also states that Naxtra-equipped vehicles can achieve a range of up to 500 kilometers, approximately 310 miles on a full charge, with the company citing figures as high as 370 miles under cold conditions. As of this report, these range figures have not been verified by an independent testing laboratory and represent CATL's own published claims. The fourth difference, and the most significant figure in Naxtra's specifications, relates to battery lifespan. A typical lithium-ion electric vehicle battery is rated for approximately 2,000 to 3,000 charge cycles before its capacity declines significantly. CATL states that Naxtra exceeds 10,000 charge cycles, representing 3 to 5 times the cycle life of a conventional lithium-ion battery. This figure suggests the battery could outlast the vehicle it is installed in. On safety, Naxtra was tested against China's GB 38031 standard, a regulation that includes crushing, drilling, and sawing the battery cell. According to CATL, the battery did not produce smoke or fire during these tests. Beyond the technical specifications, the development of Naxtra has broader implications for the global battery supply chain. In the United States, Natron Energy, a company developing sodium-ion battery technology, shut down both of its production facilities and canceled a planned $1.4 billion factory in September 2025. This was widely regarded as the most significant American effort to commercialize sodium-ion batteries at the time. Separately, LG Energy Solution, a South Korean battery manufacturer that supplies companies including Volkswagen, General Motors, and Tesla, established a sodium-ion pilot production facility in Nanjing, China, rather than in South Korea or the United States, and entered into a materials supply agreement with a Chinese chemical manufacturer to support this development. In terms of market position, CATL and BYD together currently account for more than half of the global electric vehicle battery market. Sodium-ion technology is also expanding beyond passenger vehicles. China currently operates a 100-megawatt sodium-ion battery storage station for grid applications. CATL is also expanding its battery swap network, with plans to scale beyond 3,000 swap stations across 140 cities, including more than 600 stations in northern regions of China, where cold-weather battery performance is a significant operational factor. Market analysts project that the global sodium-ion battery market will grow from approximately $1.39 billion in 2025 to nearly $7 billion by 2034, reflecting an expected expansion across electric vehicles, commercial trucking, and grid-scale energy storage applications. Taken together, these developments indicate that sodium-ion battery technology has moved from a research-stage chemistry to a component of commercial production within a relatively short period. The combination of CATL's documented investment since 2016, the 2021 product launch, the 2025 introduction of Naxtra, and the parallel setbacks experienced by Natron Energy in the United States, and the relocation of LG Energy Solutions' sodium-ion development to China, illustrate a shift in where sodium-ion battery manufacturing capacity expertise are currently concentrated. On the 13th of April 2026, a Chinese company called Geely held a press conference and announced something that engineers had spent decades calling physically impossible, not difficult, not expensive. Impossible. The number they put on the screen was 48.41%. Here is what that number means in plain English. When your car burns fuel, most of that energy disappears. It goes out the exhaust as heat. It gets soaked into the engine block. It vanishes into grinding metal parts. A normal car from a top brand like Toyota or Volkswagen only uses about 30% of the energy in the fuel you pump in. 70% is just gone wasted, turned into heat that does absolutely nothing useful for you. For over 100 years, engineers have been trying to shrink that waste, and the best any mass-produced car engine had ever achieved in history was 41%. Toyota celebrated that number like a moon landing. They spent billions of dollars getting there. They told the world it was essentially the ceiling, that going any higher would cost more than it was worth and push right up against what the laws of physics even allowed. Geely just walked past that ceiling like it was not there. To understand why 48% is so absurd, you need to understand why 41% was supposed to be the finish line. Think of a combustion engine like a campfire stuffed inside a metal box. You throw fuel in, it catches fire, the explosion pushes a piston down, and that motion eventually turns your wheels. But fire produces a massive amount of heat, and heat does not care about your wheels. It wants to spread everywhere equally, into the metal walls, into the air around the engine, out the exhaust pipe. There is a rule in physics called the Carnot limit. Here is what it means in plain language. There is a hard mathematical ceiling on how efficient any heat engine can ever be. It depends on how hot your explosion is versus how cold your exhaust is. The bigger that gap, the more work you can theoretically squeeze out, but there are limits on both ends. Make the explosion too hot, and you melt your own engine. Keep the exhaust too cold, and your pollution control systems stop working. For decades, engineers at Toyota, Honda, BMW, and Volkswagen treated 40% like a brick wall. Getting from 35% to 41% took billions of dollars and decades of patient refinement. Toyota got there using a clever trick called the Atkinson cycle, where you leave the intake valve open just a tiny bit longer than normal. That small change reduces wasted compression energy and squeezes out a few extra percentage points of efficiency. When Toyota hit 41% with their 2 and 5L dynamic force engine, the entire industry stood up and applauded. Engineers published papers stating that going significantly further was practically impossible at any reasonable cost. The prevailing wisdom was that pure electric vehicles were the future anyway, so why keep pushing a technology that was already being phased out? That assumption turned out to be one of the most expensive misjudgments in modern automotive history. Before we talk about 48%, we need to talk about 46% because that is where the story really begins to shift. BYD, which stands for Build Your Dreams, looked at the traditional hybrid car and called the whole design outdated. In a standard hybrid, the engine and the electric motor are both working to drive the wheels at the same time. The engine constantly changes, speeds it revs up on hills, slows down at traffic lights, shifts gears through a complicated transmission. Every time the engine changes speed, it drifts away from the zone where it runs most efficiently. BYD had a different idea. What if the engine did not drive the wheels at all for most of your journey? What if it just stayed at one perfect speed and acted purely as a generator making electricity? The wheels would be driven entirely by electric motors, and the engine would only ever do one job run at exactly the RPM where it works best, nothing else. The result was their DMI system, which hit 46.06% thermal efficiency on their fifth-generation platform. The global automotive press was genuinely stunned. A 5% jump in thermal efficiency sounds modest until you realize it took Toyota roughly 20 years and several $billion to gain the 5% that brought them from 36% to 41%. BYD did it in a fraction of the time with a fundamentally different approach. Legacy automakers had a quiet moment of panic. Then most of them went back to their roadmaps and told themselves this was a regional story that Western consumers would not accept it. They said the same thing about Japanese automakers in the 1980s. We all know how that ended. But while the industry was still processing BYD's 46%, Geely had already been working for 2 years on something that would make even that achievement look like a warm-up act. Geely's iHEV system did not just improve on existing engine design. It threw out the rulebook on how air and fuel mix inside a cylinder. Here is the problem with a normal engine. When air and fuel get pulled into the cylinder, they do not mix evenly. Think about pouring cream into a cup of coffee. Without stirring it, you get uneven swirls. Some spots are thick with cream, other spots are mostly coffee. The same thing happens inside a traditional cylinder. You get pockets where the mixture is too rich, and pockets where it is too lean. When the spark plug fires into that uneven mixture, the flame does not spread all at once. It starts at the spark and slowly ripples outward like a wave. And while that wave is crawling across the chamber, heat from the first burst of flame is already bleeding into the surrounding metal walls. By the time the whole mixture has burned, you have lost a significant chunk of energy to the engine block itself. Geely's engineers solved this with what they call the Huayue tornado combustion system, the fire tornado. They completely redesigned the shape and angle of the air intake channels. When the intake valve opens, the incoming air is not just pulled in passively, it is forced into a high-speed spinning vortex, a literal controlled tornado inside the cylinder. When the spark plug fires into that spinning tornado, the flame explodes outward in all directions simultaneously because the fuel and air are already perfectly blended. Almost all the energy goes straight down onto the piston before the heat has a chance to leak into the walls. But cranking up combustion like this creates a new problem: engine knock. That is when fuel ignites before the spark plug even fires, creating an uncontrolled bang that can crack pistons and destroy an engine within minutes. Solving the knock problem is what kept engineers stuck below 41% for so long. Geely's answer was to make the engine run hot and cold simultaneously in different zones, completely on purpose. In a normal car, the cooling system sends water through the entire engine at roughly the same temperature. Geely split the cooling system into 2 completely independent zones. The cylinder head, the very top of the engine where the explosions happen, is kept extremely cold. Coolant flows fast and aggressively through this zone, pulling heat away the moment it appears. Keeping the top cold means the air charge stays dense and cool right up until the moment of ignition, preventing premature detonation and allowing the engine to run at a far higher compression ratio than would normally be safe. More compression means more energy extracted from every single explosion. Meanwhile, the engine block down below, where the pistons slide up and down thousands of times a minute, is kept deliberately warm. Why? Because warmth thins out the engine oil. Thinner oil means the pistons slide with dramatically less friction. Every tiny bit of friction you eliminate is energy that reaches the wheels instead of being wasted as heat from metal grinding against metal. So you have a single engine that is cold at the top to allow massive compression and warm at the bottom to minimize friction. In traditional engine design, those two goals directly conflict with each other. Geely built a system where both happen at the same time in different parts of the same engine. The whole thing is managed by an electronic water pump that reads engine conditions dozens of times per second and adjusts coolant flow instantly. Even a 48% efficient engine is useless if you bleed that efficiency away fighting through a heavy, complicated transmission. Traditional automatic gearboxes are mechanical masterpieces, but they are also heavy and full of friction. An 8 or 9-speed automatic has hundreds of individual moving parts, clutch packs, hydraulic torque converters, shift forks, synchronizers, and the whole system can weigh over 100 kilograms. Geely looked at all of that and started from a blank sheet of paper. What they built is called the 1-1-in-1 EDHT Intelligent Drive System. Instead of a gearbox, it is an electromechanical power router. It packages the engine, the generator, 2 electric motors, the high-voltage inverters, and the thermal management hardware, all into one single compact housing. The total powertrain weight dropped by 13.5% compared to traditional hybrid setups. For about 90% of your daily driving, the combustion engine has zero physical connection to your wheels at all. The engine runs at its perfect efficiency sweet spot and powers a generator. That electricity goes either to the battery or directly to the electric motors spinning the wheels. From the driver's seat, the whole experience feels like a fully electric car: silent, smooth, instant torque. The only time the system physically connects the engine to the axle is at steady high-speed highway cruising. At around 80 miles per hour and above, routing power through the electric motors actually wastes more energy than a direct mechanical connection, so the system automatically locks the engine to the wheels, bypassing the electrical conversion entirely. Managing all of this is an AI system that recalculates the most efficient way to route power 50 times every single second. It reads your navigation map, spots a hill coming up 3 kilometers ahead, and decides in real time whether to charge the battery now and coast down the other side, or use the battery now and let the engine recharge on the descent. The combined result of all of this, the fire-tornado combustion, the split thermal zones, the 1-1-in-1 drive unit, and the AI power routing, is a certified fuel consumption figure of 2.22 L per 100 kilometers. That is a Guinness World Record for production vehicles. On a full tank, you are looking at a range of over 2,000 kilometers. And this is not a small lightweight commuter. This is a full-size SUV burning less than 2.5 liters per 100 kilometers in real-world conditions. Pure electric vehicles are genuinely great in the right conditions: silent, efficient, zero tailpipe emissions on the road. But they come with real trade-offs. A large electric SUV needs a battery pack that can weigh over 500 kilograms. Charging infrastructure is still thin across huge parts of the globe, and range anxiety is a real practical barrier for real people with real lives. What Geely's system offers is a completely different path. You get the smooth, silent, instant torque, daily driving experience of a fully electric car, but your total range is over 2,000 kilometers. You can fill up at any petrol station on the planet, and the fuel cost per kilometer is comparable to a pure electric vehicle in most markets. The internal combustion engine was invented in Europe. Germany, France, and Britain dominated it for over a century. Japan refined it to what everyone thought was near perfection over 50 years. The efficiency record now belongs to a company that did not have a serious global automotive presence 15 years ago. Closing that kind of gap is not something you do with a firmware update or a new advertising campaign. It requires rebuilding engineering pipelines, asking different questions, and funding years of research. Legacy automakers are now caught between investor pressure to go fully electric and combustion technology that is falling further behind at the same time. But for consumers everywhere, that competition is good news. History shows that when engineering ambition like this enters a market, prices drop and technology improves across the board. What Geely has proven beyond any single number is that the combustion engine still had enormous life left in it. The limit was never the laws of physics. It was the limits of what people believed was worth trying.